Well, hello everyone. My name is Simon Foster. I'm from the University of York. I'm going to be presenting our paper, Formally Verified Simulations of State-Rich Processes Using Interaction Trees in Isabelle HOL. This is joint work with Professor Chung-Il He from Seoul National University and Professor Jim Woodcock from York University as well. So interaction trees are co-inductive structures with potentially infinite breadth and depth, which are used to represent the way a process communicates with its environment and evolves over time. They're used to give formal semantics to programming languages, and here we're going to be showing how we can develop verification and simulation support in Isabelle for them. We can use interaction trees to encode symbolic label transition systems for a variety of process algebraic languages, and crucially, interaction trees are executable. And that means that they are applicable to the production of verified simulations and implementations. Now, interaction trees were previously mechanized in CONCUR and have been applied in several program verification projects. The contributions of this paper are a novel mechanization of interaction trees in Isabelle HOL. This requires some quite substantial adaptation of the CONCUR implementation. We provide an iTree-based semantics for deterministic CSP and circus processes. This includes a formal link with the standard failures divergences semantic model. And we provide a method for generating animations using the Isabelle code generator. So first I'm going to explain what an interaction tree is. So we describe an interaction tree using a co-data type. So this is a kind of way of representing co-inductive structures in Isabelle. We fix two types for events and for return values. And then we define an interaction tree using three constructors. So the first is a return, meaning that we terminate returning a value in R. We can do an invisible silent event, right? So sil, and then we behave as a successor interaction tree. And finally, we have visible events, right? And here we have a partial function. So this arrow here means a partial function from events to interaction trees. And so the idea is that every event can have a maximum of one continuation that may follow it. So this is kind of like a menu of possibilities. Right? So these are the enabled events and then the interaction trees that occur after this event is chosen, should it be chosen. We introduce some notation for interaction trees, tick v for returning a value v, tau p for silent events, and this kind of notation for a choice. So what this means is that we pick some e in a set of events e, and then we behave as p of e, right? Which is represented by this. So this is a partial function here, right? Partial lambda abstraction where the domain is e. So here are some examples of finite interaction trees. So this interaction tree performs 3 tau events and then terminates, returning the value 5. This is a deadlocked interaction tree. So this is an interaction tree with a visible event, but the visible event function here is empty, right? So it's an empty partial function. That's how we represent that. So no events are enabled, and therefore we are deadlocked. And finally, this is a kind of process algebraic interaction tree. So we've got 2 choices. We can either do an event A, and at that point we we perform a silent event and then return the value X, or alternatively, we can do the B event and then we deadlock. Right? And all of these things can be represented using interaction trees. Of course, since these are co-inductive structures, they can also be infinite. And we can construct infinite depth interaction trees using primitive co-recursion. So this is an example of a primitive co-recursive definition. We give it a type, it's an interaction tree, a prim co-rec, where we have this equation here. So div equals tau of div. Now, of course, if this was a recursive definition, this wouldn't be valid because it doesn't terminate. But because we're in the world of co-data, we can have infinite things very easily. One thing we require, though, is that such definitions are productive. So that means that all equations in a prim co-rec must guard the co-recursive call with a constructor. So for instance, in this case, div is guarded by tau. And that means that we can always unfold it one step, right? So even though it's infinite, we can step through it, which means that we can compute with it. And we can relate infinite I trees by constructing by simulation relations and weak by simulation relations. The details are in the paper. So now I'm going to explain how we use I trees to give a semantics to CSP. So CSP, I guess it's a language we're all familiar with. So you have channels, you have processors communicating with each other using these channels. So you can input values, which is what this represents here. We can output values, and inputs and outputs match up with each other, and we have parallel composition. We have external choice, so we can have sequential processes that make choices between different events, and so on and so forth. Right, so here's a simple example of a CSP process. It's a buffer, very simple example. It's a parametric process where the parameter buff represents the current state of the buffer, so it's a list of integers in this case, and then the body is a choice, right? So we can either input a value x over the input channel and then behave as buffer where we've added that input value onto the end of the state, or if the length of the buffer is greater than 0, then we can output the head and then remove the head from the buffer and recursively continue in that way. So in this paper, we're going to allow us to characterize the semantics of such processes, but we focus on processes that are deterministic. So this is an example of a deterministic process, right? So when you have this choice here, you can either choose an input or an output, right? So the same event can't occur on either side. Whereas a process like this, A then P, choice A then Q, is excluded because A can either go to P or Q, and so we're not going to allow that. We encode variants of all the operators above that enforce determinism. We can't show all of them because there's not enough time, but they're all in the paper. So what I'm going to do is I'm going to give a brief overview of some of the operators that we've encoded and how that's done. So we're going to think about basic processes communicating over channels. And in our Isabelle mechanization, we model channels using prisms. If you don't know prisms, they're a well-known concept from functional programming. Essentially, prisms give us an abstract way of characterizing the constructors of an algebraic data type. So an algebraic data type has several constructors associated with it, which can carry parameters, and prisms allow us to characterize each of these parameters. So a prism, C, so V, we have this kind of funny arrow notation because we're talking about prisms, so that's why the triangle means. V is going to be the value of data that this channel carries, and E is going to be the type of events, right? And we characterize prisms using two functions: a build function that allows us to build an event over a channel, and a match function that allows us to destruct an event from a particular channel. Of course, the latter is partial because we may have several possible channels, and so we have to know that we're applying match to an event of the correct kind. Now, once we've got these, we can now begin to construct some interaction trees for CSP processes. So here is an interaction tree constructor for an output event. So it takes a channel of type V in the event set E, a value which we're going to send over that channel, and it produces an interaction tree. And this has got an empty return associated with it. And that's because there's no value that we're returning, right? Because we're doing an output. And so the way that we represent this is that we have a singleton visible event, right? So we just have this single maplet here. So we're going to allow the event C carrying the value V. And then after that, we're going to behave as ret empty, which basically means we terminate. So what does this mean? So we output our event and then we terminate, and then we can potentially move on to do something else. An input event is a little bit more involved than this, but it's basically the same concept. So again, we have a channel. We're going to allow us to restrict the domain of values that we're going to allow to receive. And in this case, we're not going to produce an empty value. We're actually going to produce the value that we input, right? So this can then be passed on to a successor. And so the way this is represented is as a partial function whose domain is going to be the domain of the match function. So we're only going to accept inputs over this channel, which is what that means. And we're also going to restrict ourselves to this set A. And so we accept an event over this channel, and then we destruct that channel using match, and we return the value, right? So you input a value and then you return it, right? And then that can be used by a successor. So of course, this assumes that we can then sequentially compose things together. And the way that we can sequentially compose things is by using a monad. So we've defined a monadic bind operator, P, then Q. So P here is an interaction tree, and K is what we call a Kleisli tree. So it's a function from a value to an interaction tree. And so the idea is that P executes until it returns a value, and then it passes that value on to K. It's defined as a primitive co-recursive definition. I won't go through it in detail because I don't have time, but essentially the idea is that tau events, you're just going to kind of skip over those, right? You're just going to kind of push them out to the front. Visible events the same, but when you come to a return value, you're going to pass that return value onto the continuation K. Now, if P, so the first argument of the bind doesn't terminate, then P bind K is going to be equal to P. So for instance, if P is stop or div, then that's a left 0 for bind, right? Now, using this operator, we can now define the actual core output and input events by using a bind. So for instance, this one, when we first of all output a value over C, and then we behave as B. So how do we do this? Well, we first of all do the output, and then we bind that to the function which behaves as P. And similarly for the input. So we input the value, and then we pass it on to P, the continuation. Now, as I said, we've encoded all the operators of CSP in this one, but I can't go through them. But what I'd like to just summarize very briefly is then how we link this kind of semantics to the standard failures divergences model of CSP. So what we do essentially first is we characterize a big step operational semantics. So we have a transition relation that says that P can evolve to become P primed over some sequence of events TR, which is what you've got here. And we have these production rules. So we encode an inductive relation, which gives a characterization of big step operational semantics for any interaction tree. We then can characterize Bill Roscoe's transition relation, which he defines in his book, Understanding Concurrent Systems. I can't go into detail again, it's all in the paper. But then from that, we can describe all the parts of the failures divergences model. So we can define the set of traces of an interaction tree. We can define the set of failures. So these are the partial traces where you arrive at a state where you're willing to accept a certain number of values. And we can define the divergences. So these are the traces that lead to infinite tau behavior, right? And we've shown that these characterizations satisfy many of the important properties of the failures divergences model. So I want to conclude my talk by talking about formally verified simulations. So Isabelle's code generator allows the production of code from Isabelle definitions in Haskell, Scala, and SML. So the way this works is you can define a function or a co-recursive definition in Isabelle, and then the code generator will produce code in the target language, in this case Haskell. Right? So this is the append function, of course, and the equivalent in Haskell. So these definitions can depend on library functions, but this requires trust. So the code generator is very principled. So it will code generate for everything potentially, every definition you make. Or you can say, well, I'm going to trust this function, so I'm going to make use of it. And that means that you get more efficiency, of course, at the expense potentially of trust. So what we do in our work is we allow animation via code generation. And this is a really nice feature of interaction trees. So essentially what we do is we first of all, construct an iTree-based CSP process in Isabelle, and then we use the code generator to generate equivalent Haskell code for that. And we can do that because Haskell has lazy evaluation, and so it can represent infinite structures very naturally. We need to employ data refinement to provide an executable implementation of partial functions. Again, the details are in the paper, and that's just because things like calculating the domain of a partial function isn't always decidable, and so we have to come up with a kind of restricted subset of partial functions, which is decidable. And we then leverage lazy evaluation to allow stepping through interaction trees. So what I'm going to do now, just briefly, is to give an example of how this works. Okay, so here we are in the Isabelle environment now. So we've got a theory, Isabelle theory called buffer underscore CSP, which is going to be the buffer example that we looked at earlier. And so what we're going to do is we first of all define a type for all the channels that we have. So we have, we can input an integer, which is going to go into the buffer. We can output one, which can be taken out of the buffer. And in addition, we can also query the state, right? And this is going to be useful during animation, just so that we can see what values are in the list. We represent this in a slightly different notation to what we saw earlier, although we can support exactly the same notation. It's just slightly easier to show it desugared at this point. So we have a loop, right? So we have a kind of looping thing. So we're defining it as a tail recursive definition. And then we have all the possibilities that can occur, right? So here we can input over the in channel, and we return the updated buffer as before. Or alternatively, we have this kind of guarded definition where we say that if the length of the buffer is greater than 0, then we're going to output the value that's at the head and return the tail. Or thirdly, we're going to allow it to query the state, right? So we can look at the current value of S, right? And then we don't change the state otherwise. So this is the definition of our buffer. So now what I can do is, so I have this command that we've developed called simulate. And so when you go to it, so what happens in the background is it generates code, right, for all of this in Haskell, and it then inserts the animator into that code, right? And then if I click start simulation, so GHCI loads up at the bottom with the simulator. And then what I can do is I can do simulate, simulate buffer. So there's a technical thing here, which is we're having to restrict how many values, the kind of set of values that we're going to allow. And that's just to make the animation displayable, right? So you can display all of the possibilities, because of course, if we had an infinite number of possible values, you wouldn't be able to display it. So we give that set, which in this case is 0, 1, 2, and 3, and we give the initial value of the buffer empty, and we run the simulator like this. And now we can see where we can actually simulate this interaction tree, right? So it gives us all the options there at the bottom. So I'm going to input a value into the buffer by selecting number 2. I'll put in another one, put 1 in, and then I put, let's put a 3 in. And you can see that the buffer is being updated, right? So you can see the state there is changing. But then I can start to output things. So I output 0, and it goes down to 1, 3. And then I output 1, and so on, and then the buffer's empty, and we're back to where we started again. Right, so this shows then how we can go right from this iTree-based representation into something that can be simulated, and potentially something that we can use in an implementation, right? Not necessarily a very efficient implementation, but a correct implementation nevertheless, which is quite useful. Okay, so I'm going to conclude now. So we've adapted the COC mechanization of interaction trees to Isabelle HOL. We use them to give us semantics to CSP and Circus as well. We didn't show the implementation of Circus, we didn't have space, but Circus is like CSP, except it has state variables, and so we can also represent those, which is quite nice. We applied the code generator to the production of animations, and I hope you can see that this process is pretty much automated, right? All that you have to do is feed in a process definition, and then the animation just pops out using the code generator, and that's very nice, right? So there's lots of applications, I think, that we can apply this to. So where you want to take a formal model and simulate it, right? Often we can only verify it, but simulation is a really useful technique that people can use to understand the formal model and to find corner cases and so on. So things that we're going to be applying this to in the future is we've got this language RoboChart that's developed at York, which is a modeling language for robotic controllers. And at the moment, we're developing a semantics based on CSP on top of this interaction tree animator, which means we can then animate robotic controllers and potentially insert them into kind of 3D simulations of them in the future, which would be very nice. In order to make this work, we'll need to consider more efficient implementations of partial functions. At the moment, we're using associative lists, but there are better implementations out there. And we also need to consider non-determinism, which we have various ways that we can think about that. There's more information in the paper. And also we'll need to think about real time in the future. So thank you for listening. Here are some useful citations. The code is all available on GitHub at the bottom there. And thank you for listening. Goodbye.